Imagine reading an amazing book, but by the time you hit the period at the end of a sentence, you've completely forgotten the very first word. Crazy, right? Well, early AI had exactly this huge memory problem. It literally forgot the beginning of a sequence before it even reached the end. So today, in this explainer, we're going to break down this massive glitch that stopped AI from reading or writing properly, and we'll look at the brilliant hack that finally gave it a memory.
Okay, let's dive right into this. To really understand how we got to the incredibly smart chatbots we use every day, we have to look back at the core problem of processing sequential information. You see, when early AI models were asked to process a sequence, like just a string of words in a sentence, they hit a massive brick wall. They simply couldn't hold on to the context of that sentence for more than a few words at a time.
And this glitch was a total roadblock. Think about it. Human language relies entirely on context and sequence. If I say, I grew up in France, so I speak fluent, you automatically know the next word is French, right? That's because you remembered the beginning of my sentence. But early AI? It completely lacked this long-term context retention. It would just stare at a blank space and guess wildly, all because the word France had already completely faded from its digital brain. To solve this, researchers introduced our first major architecture. Section 1, the RNN bottleneck and its short-term constraints. Way before the modern tools we have today, we had something called the recurrent neural network, or RNN. Now, what made the RNN special back then was its feedback loop. It didn't just process a word and toss it in the trash. Whatever output it generated from its hidden layer was passed back into the loop sequentially for the next step. It was purpose-built for sequence-related data, but, and this is a huge but, it had a fatal flaw. It was strictly bound to short-term memory. Let's visualize how this fading memory actually works. Picture a sentence moving one by one through a chain. The movie was amazing because the ending was emotional. Okay, step 1. The word movie is processed. Great. Step 2. Amazing is processed, but movie starts to fade. By step 3, as the sentence grows all the way to the word emotional, the critical early context, the fact that we're even talking about a movie, vanishes completely. As the sentences got longer, all that important early information was entirely overwritten, gone. Obviously, AI researchers knew they needed something vastly smarter to handle human language. That brings us to Section 2. Enter LSTM, the ultimate solution. The sheer elegance of this new solution literally changed everything. Researchers created long short-term memory, or LSTM for short. This was an advanced neural network architecture designed specifically to sustain both immediate short-term dependencies and long-term memory across massive sequences. Basically, it was built to remember what actually mattered for a really long time. But how did it actually pull this off? Let's take a look under the hood. Section 3. Inside secret gates, controlling data flow. Unlike the old basic RNN, inside an LSTM, you'll find active decision makers. We call them gates, and they totally control the flow of information. There are 3 of them, and guys, this is where the absolute magic happens. First up, the forget gate. It looks at the incoming data and literally decides what information is useless and just throws it away. Second, the input gate. This one decides what new, valuable information actually needs to be stored in the memory. And finally, the output gate decides what stored information to use for the current prediction. These 3 specific gates are exactly what connect the short-term memory to the longer sequence. You can kind of think of them as bouncers at an exclusive club. The forget gate kicks out the irrelevant data. The input gate lets the VIP context inside, and the output gate escorts the right information to the front exactly when it's time to speak. But these gates don't just work in a vacuum. They serve something much bigger. Moving on to Section 4, the power of cell state, the core engine. Okay, so if the old RNN was like a winding, congested dirt road where data easily got lost in a short-term memory bottleneck, the LSTM introduced a long-term memory highway. We call this high-speed lane the cell state. The cell state runs straight down the entire chain of the neural network with only very minor linear interactions. Because of this, information can easily flow along it completely unchanged. So, the absolutely crucial takeaway you need to remember is this. It carries important long-term information across the entire sentence. Because those bouncer gates are carefully regulating what gets added or removed from this high-speed lane, the really critical context actually survives the journey. Retaining this longer context was an absolute game changer for AI comprehension. And by finally solving this sequential memory problem, LSTMs changed the trajectory of machine learning forever. Section 5, paving the way for GPT, the next generation. Now, while LSTMs were a massive breakthrough, processing words sequentially one by one was still super computationally heavy. It took a lot of work. Then, in 2018, everything shifted again. Google published a wildly prestigious research paper titled "Attention is All You Need." This paper introduced the transformer architecture, which eventually replaced LSTM cells altogether by processing all the tokens in a sequence in parallel rather than one by one, using something called self-attention. Let's see how this all builds across the timeline. We started with RNNs and their simple, highly flawed feedback loops that evolved into LSTMs, which brought us cell states and gates to fix the memory wipe issue. And that directly laid the groundwork for transformers to process data in parallel, ultimately giving us the modern large language models we use today, like ChatGPT. Every single step here was a crucial stepping stone to generative AI. It is just wild to think that a few years ago, an AI couldn't even remember the start of a basic sentence. And now, thanks to the groundwork laid by the LSTM forget gate and cell state, it can generate entire codebases and books with perfect context. So I'm going to leave you with this provocative thought. If LSTM gave AI its first real short and long-term memory, what will the next generation of AI be able to remember about you? Let me know your thoughts on this, and if this explainer finally made sense to you, drop the word memory in the comments below. Keep learning, and I'll see you in the next explainer.